All right, so let's go ahead and get going. First question: any issues or questions with PA1? Have not seen many people in office hours. Had nobody today, so I'm taking that as a good sign. But if there's any questions, go ahead and speak now. All right. Next point is with Git. There's people who are getting tripped up on Git because they pushed the wrong repository or they named it the wrong way when they did their Git remote add origin and so on and so forth. So a couple of things to keep in mind. Again, number one, best policy. Every time you start a new project, new assignment, anything like that, start in a completely clean directory on the Linux machine and push over to a completely new repository on GitLab. Okay? Don't try to do all of 223 from one repository, because when it comes to submitting, it's going to get tangled up. So you're doing PA2, start in a new directory. You're doing a test project, start in a new directory. Okay? Try to keep things really clean and organized that way. If you inadvertently mess something up, right, you can always delete the repository on GitLab, go in a completely new directory on Linux, just copy the files over that you actually care about, and just do another git init, git add, git commit, git remote add origin, git push origin master. Okay? And again, the best way to avoid getting tangled up with any of this is day one, as soon as you start a new project in a new directory with a new Git repository, push it over to Git right then and there, and hop over to GitLab and add me as a reporter. Okay? I can't say that too many times. Do that the first moment that you start a project and you don't have to worry about it again. And then just write your files, git add, git commit, git push origin master. I'm going to take away the restriction on PA2 about only having your one.java file, because I realize that's kind of a complication Git-wise. So I'm going to let you push over whatever you want as long as your required file is in the top level directory. So on PA2 that will simplify things. All right, so let's talk some Java. So one of the key things about Java is, we're working with objects. Okay, and we want to think of objects as more than just variables. We want to think of them as coming with code embedded in. And this is what PA2, which we'll talk about tomorrow, is going to be all about, is thinking about objects as this conglomeration of data and code. Okay, but I want to start working with that concept today, and I want to work with this using some classes that are already available to us. And we're going to start with, maybe our favorite data structure, which is a linked list. So in Java utility, we can import this class called LinkedList, and it implements a linked list like we built by hand in 222. And linked lists in Java come with a bunch of methods that we can use. So we can add something to the end of the list using the add method. We can insert something at a particular position in the list by using the add and specify an index. Okay, this is more than we could do with our linked list from 222. We can actually place things in the middle of the linked list. Okay, we can add something to the beginning by using the add first. We can add to the end by specifying add last, which is the same thing that add does. We can zero out the list by saying clear, and so on and so forth. So you can look through this documentation on linked list and see all of the features that are available in this object. Okay. Some other features that we didn't implement in our linked lists will let us take an index and retrieve the nth element from our linked list. So we can use our linked list kind of like we use arrays, right? We can place things at particular positions. We can retrieve things from particular positions. So it's a super duper linked list. We can search for things. We can say index of, and it will tell us the first place in the list where this thing occurs, or it'll give us -1 if it doesn't occur. And linked lists are part of a bigger picture, right? For example, we have push and pop, which is something we normally think of for stacks, right? Well, we've said we can implement stacks with linked lists, and so if you think of a linked list as a stack, push and pop do what you would expect them to do. We can remove from the head, right? So we can treat them like cues. And we can turn them into arrays, right? Which is kind of handy. So the linked list class is a really, really powerful class, and you want to be familiar with it, because anytime that you think you might want to use a dynamically sized array or a stack or a queue or anything else like that, you can go to a linked list and get pretty much everything you need, and probably a lot more. And it's worth noting that a linked list is actually an extension of an abstract sequential list, which is an extension of an abstract list, which is an abstract collection, right? Which is why there's so many things, so many goodies inside this class. So to play with linked lists, we have to introduce a new concept, which is called a generic. Okay, and here's the idea. When we wrote our linked list code in 222, we were working with integers. Okay, and we had to set up a node, and we had to look at the next field, and we might have had a sentinel, and we adjusted pointers, this thing arrow next equals new, and so on and so forth. All of that code really had nothing to do with the fact that this was a list of integers. And if we had implemented a linked list of strings, the code would have been almost identical. Okay, the manipulation of the pointers, the creating of a new node, the adjustment of the sentinel, all of that stuff would be the same. So in Java, you can create a class that works with different types of data. Okay, 222, we made a linked list that worked with integers. Java, we can create a linked list and we can specify, do we want this work with integers or do we want it to work with strings? Okay, so this is called a generic, and a generic is just a slight twist on the syntax. Basically, when you declare or construct an object from a class like linked list, you have to specify what kind of object this list is going to work on. So let me just do some code for this. So let's do LL test. And we'll do our public static void main. And we'll do our import java.util.linkedList. And let's create a linked list. So we're just going to call this thing, if I was in class, I'd get somebody to pick a name. I just call it my list. So linked list is the type of object that we want. So linked list, my list equals new linked list paren. Okay, so we're constructing a list. Here's the generic part. When you look at the documentation for linked list and you look at the constructor, when you look at the header up here, linked list, angle bracket E. Okay, that angle bracket E, that E gets replaced by what type of object you want to work with. So our syntax, let me comment this one out and put in the real syntax. This is going to be linked list angle bracket integer. My list equals new linked list angle bracket integer. And we don't have any arguments for the constructor. So this is how we construct the list. Okay. So let's construct a list and let's specify the type of data to store. So we're saying this is a linked list of integers. So let's add some stuff. So we'll add some prime numbers to our linked list. And then let's look at the list. So how can we look at it? Here's the method summary. We could say how many things are in the list by doing our list.size. And we could say, let's retrieve the element at a particular index. So let's play around with that. And so I can print the size of my list by just saying, you know, mylist.size. And then let's iterate over those. So we'll say element I of the list equals, and then we'll do mylist.get parentheses I, which will retrieve the ith element of the list. And that's our whole test main program. So just, you know, junk code here just to explore. LL test. And then we can run it, and it pulls back the elements of the list, tells us there were 5 things in there, and it pulls them out, and they're in that right order. So with a piece of code like this, you can explore any of these classes. For example, we're playing with linked lists right now. Suppose we want to insert things into the beginning of the list. So we could say put, yeah, I don't do this often. Let's, there's a get, there's a, okay, let's add first. Okay, so let's add to the beginning of the list. So instead of just saying add, let's do add first. So compile that and run it. Well, now we're getting our things in the inverse order in which we added them, because the last thing we added was a 13. We put that in the beginning of the list. So now, you know, the first thing in the list is the last thing we added. So this is a LIFO, right? Or a stack maybe. So 13, 11, 7, 3, 2. Wow, I skipped 5. I don't know why. That was goofy. All right, so write junk code, right? Code that you don't plan to turn in or necessarily keep, but code that just lets you explore the ins and outs of, you know, some aspect of whatever it is you're trying to learn. In this case, the different methods and constructors for a linked list. And, you know, if I were to go up to, you know, less than or equal to the size of my list, I can compile that fine, but when I try to access element 5, I get my good old index out of bounds exception. Index 5, and it's telling me my list only has a size of 5, and so index 5 would be the 6th element, and that's out of bounds, and it's telling me this is right at line 21, which, you know, is where I do my print. All right, so linked lists. So I'm going to try to keep copies of my code so I can push them over to the server when we're done. So let's make a new program, linked list test 2. And this time, let's make it a linked list of strings. That's all we got to change. Now it's a linked list of strings. So we'll do add first goodbye to put some things in the beginning. Our print code doesn't have to change. So let's go ahead and compile that. And I typoed. So LL had an uppercase T. Let's compile that, and then let's run it. And there's our strings in inverse order. Right? Goodbye fun is this hello, and I still went up to less than or equal to, so it still throws the exception. But right, if we just went up to less than, right? So now we've got a linked list of strings working. And we used integer, we used string. We could use anything that we wanted. Okay. So a couple of ideas here. So let's write these out. All right, so key idea is 1, generics, which is this idea of linked list, angle bracket, and then the type of object that you're going to work on. So this is a class name. Okay, and it can be any object. Okay, it doesn't have to just be integer or string. It can be an object that you wrote. 2, this is a linked list of those objects. Okay, what do I mean by that? Let's look at our linked list of strings, right? So I can say mylist.get parentheses I. Yeah, that's returning the word hello or is or goodbye, right? But this thing that I'm highlighting right here, this is a string. Okay, it's a string in the sense that that it's an object that supports all of these methods. Right, so since this is a string, I could do the following. So let me make another version. So this thing is a string, mylist.getI. I could call the toUpperCase method on it. Put some space in here. So mylist.getI is a string I can call toUpperCase on it. And since strings have a toUpperCase method, the result of this will be the uppercase version of the ith element of my linked list. Right, so now I get my uppercase version of the elements. And that may not seem significant in the case of strings, but it's going to be really significant in the case of PA2. Okay, because the things in this list are, objects. They have methods associated with them. If I want to know the length of these things, I could do mylist.getI.length paren. So let's make this even more interesting. So remember our rectangle class, okay? So our rectangle class, we had height and width, and they were doubles. We had our constructor. We could construct with 2 arguments. We could construct with no arguments to make a 1 by 1. We could construct with a single argument to make a square. And we had checks to make sure we didn't have, negative dimensions. And we had area and perimeter methods. We had accessors and mutators. And then we had a toString method. Okay, and the toString method prints out the word rectangle, and then it prints the height and the times and a width. So if we have a 5 by 7 rectangle and we try to convert it to a string, it'll say rect : 5 by 7. Okay, so that's our rectangle method, our rectangle class. So let's make a linked list of rectangles. So how do we do that? when we declare and construct our linked list, we just say linked list angle bracket rectangle. Let me just go back to the add method so we get these things in order. So what should we add? Well, we have to add a new rectangle. So let's add a new rectangle. Let's add a 5 by 7 rectangle. And let's add a default rectangle, which is just going to be a 1 by 1. And let's add a square rectangle, which is going to be 7 by 7. And I don't know what people's favorite rectangles are. I usually go with a 5 by 7. Let's go with a 2 by 4. Which is not really 2 by 4 anymore. So we're adding rectangles to our linked list, right? Is that crazy or is that cool? I don't know. It's up to you. We'll print out the size of the linked list. We'll iterate through, and we will print out mylist.getI. So let's compile LL test 4, and this has to be a rectangle. And then let's go ahead and run it. And there's the elements of our linked list. Element 0 is a rectangle 5 by 7. Element 4 is a rectangle 2 by 4. So now we're rocking with a linked list whose elements are these other objects that we created ourselves that have a height and a width and so on. And all we had to do was change this specifier when we declared mylist, and also change it when we constructed mylist. And everything else kind of works for free. So hopefully that seems, I don't know, reasonable, interesting, useful, something. So what else can we do with this? Right, so element I of the list is, and we'll print out what it is, whose area is, and we'll call the area method, and whose perimeter is, and we'll call the perimeter method. I hope I have a perimeter method. Right, again, since this is a linked list of rectangles, this thing, mylist.getI, is a rectangle. Anything we could do with a rectangle r equals new rectangle, we can do with mylist.getI. So there you go. So what this means for us as programmers is that when we create a class like rectangle and we endow it with all of these methods and fields and such that are useful for dealing with rectangles, we can utilize those anytime we have a rectangle, including if that rectangle is coming out of, say, a linked list, right? So we start to think of the world in these chunks, right? We want to do something with rectangles, but once we have a rectangle, we just use its methods to like find its area or its perimeter, or we use its toString method, here, to concatenate it to a string and get this nice clean output that says rectangle 5 by 7. All right, let me go back to LL test. So this is just adding elements into the list in reverse order. And let me rerun that. Let me show you a slightly different version of this. So we had an iterator, you know, a loop that would go through and print out each element. Suppose we just say mylist equals, and we concatenate mylist to that. So mylist is an object. Every object can be converted to a string, right? It's a linked list, so we're using LinkedLists toString method. We haven't written that. But let's just go ahead after we've added these 5 numbers to our linked list. Let's go ahead and print out what my list is by just appending it and calling print line. And when we do that, we get something that looks like a list. We get a pair of square brackets with the elements inside separated by commas with spaces after them except for the last one, right? So this was like the traverse code that you would write in 222 for printing out the contents of a list. It's built into the linked list class, okay, which is really cool. So again, we got that nice line of output here, right, showing us, you know, on one line all the elements of this list just by doing this. Just print out my list. And it's not magic, right? It's simply calling the toString method in mylist, which somebody in linked list, which somebody wrote to do what we did with our linked list: go through from node to node and string them together in a big string with commas in between them, and put brackets at the beginning and the end, and don't put a space in after the last one. So if we go back in here where we were dealing with strings, right, same thing. We can just print out my list by concatenating it to a string. And then when we run that, it tells me my list is, and there's our 5 strings inside square brackets. All right, and this works with rectangles as well. So I can print out my list equals and concatenate my list to it. And down here, there's our nice traversal of our list, showing us the 5 elements separated by commas inside square brackets. All right, and this is going to be the whole drill for PA2. Okay, you're going to be working with fairly complex structures. You're going to have classes that contain other classes that contain other classes. Okay, but those classes are going to be things that already exist. You're not going to have to write them. You're just writing a top-level class, but it's going to be a fairly complex structure. You're actually going to implement a hash table, which is keyed off of strings and whose data values are linked lists of integers. Okay, and we'll talk about it in detail tomorrow, but that's where we're going with this. All right, so hopefully this is making some sense. Let's keep going. So let's talk about hashes. So in Java, there's a thing called a hash map. It comes out of java.utility.hashmap. This is an implementation of a hash table. Okay, so we did hash tables. We talked about hash tables in 222. I don't think we actually coded them. We did pieces of them in ODPs. But there's a full-blown implementation of a hash table inside Java. So the main things that we do with hash tables is get and put. Okay, we can construct a hash table. We can put a piece of data into it. And remember, hashes, they work with pairs of data. So a hash is like an associative array. So we can say, let's put a key value pair. And we can think of this as something like, hash bracket key equals value. So an array is like a hash where all of our keys are consecutive integers. But a hash is like a general version of an array where we can index off of anything that we want, integers, strings, whatever, and associated with each key, we can store a value. So to put things into our hash, we just say put, here's the key I want to store it at, here's the value I want to store. If we want to retrieve a piece of information, we can say get and specify a key. And it'll return a value associated with that if it exists. Okay, so we're on the other side of things now from Winter, right? We're using these data structures. We're not actually writing them ourselves. We will later on. We'll look at how to write, lists and trees and things like that in Java. But for now, we're on the consumer side. We're on the other side of that firewall where our interface to the hash or whatever data structure is through a very well-defined set of functions, okay, which you can find in the Java documentation. We have no idea how this hash is implemented. We don't even know if it's really a hash. It could just be a big array and somebody's searching through every single element for the key that we're specifying, right? Or it could be, sending text messages to someone with a big whiteboard who just writes down your data and then retrieves it when they get a message saying, hey, give me this value, right? Makes no difference to us. Our program is only going to interact with the hash through these methods and through our constructor. And the details are hidden from us. Okay, again, this is one of the two key ideas of object-oriented methodology is information hiding, right? We don't know what the hash function is. We don't know if this is built on an array or a linked list or something else. We don't know how big that underlying array might be. Those details are hidden from us and they're not relevant to us. Okay, all we know is if we say, let's put a value associated with this key, right? It will replace that key if it exists. If it doesn't exist, it will create it for us. And if we say get and we specify a key, it will find the value associated with that, or if there is no such key stored, it'll return null. And there's other methods we might want to use. We can remove an object from there by saying remove and specify a key. We can replace, and we won't talk about iterators for now, but we will later. But there's a way we can say, go through the entire hash and show me everything that's in there, one thing at a time. So if we wanted to iterate across the elements of a hash map, we can do that, okay? But we have to use a different set of machinery called an iterator, which I don't want to get into today. So let's just write some code and play around with hash maps. And like linked lists, hash maps work with a variety of objects. So there's actually two things you need to specify. What type of object are your keys and what type of objects are your values? So let's write some code. So I'm going to import HashMap, and I'm going to say HashMap, and let's use keys that are strings, and let's use data that's an integer, and we'll just call this, I'm just going to call it hash equals new HashMap. And it'll be a string and an integer. All right, so there's a hash map ready to go. So let's put some values into it. So we'll use this put method. We can specify a key and a value. So our key has to be a word. So let's store a 13 with hello. Let's store a 7 with cool. Let's store a 0 with bye. We'll just leave it at that. Right. So we'll just pull some values out using hash.get. So hello should give us 13, bye should give us 0, haha should give us null. Try to get my parentheses right. And there you go. Value of hello is 13, value of bye is 0, value of haha is null. Now, if you want to really play with this, right, write a more interesting main program, maybe that lets you enter names and values and stores them, and then you know, lets you specify a name and pulls back a value, right? Because I'm just doing a few tests hardwired here, but just trying to give you an idea of what we can do with this. So let's modify this. Let's make a hash that is keyed off of strings and also stores values that are strings. Alright, so now we're storing data associated with those words, but the data we're storing are strings. Make sure it's called the right thing. Right, so value of hello is there, value of bye is for now, value of haha is still null. So there's a hash, right? Which you know, in other quarters we've spent 2 weeks writing hash functions and so on, and we've got them for free in Java, which is pretty cool. We've got them in a very generic way where we could, you know, have anything we wanted for the type of key and the type of data. And what happens if we try to print a hash just by appending it to a string? We get a description of our hash as follows. Curly brackets, because this is a set, it's unordered. So what's the contents of this set? Well, there's a word hello, which is associated with there. There's a string cool, which is associated with stuff. And there's a string bye, which is associated with for now. So HashMaps have a toString method that is sufficient for us to actually see the entire contents of the hash map. So that's pretty cool. I really wish I could like be standing in a classroom, because people are either getting this and your gears are whirling at things that you could do with this and how this is going to change your programming experience over the next few weeks, or this is just kind of, you know, me talking and not really registering. And I don't know which one is going on, but we'll figure it out over time. But you know, if there's questions, please interrupt and let me know. Otherwise, I'm going to assume there's some degree of the former experience going on right now. Let's take it a little further. Let's make a hash test 3. And let's have rectangles associated with strings. Alright, so we got a pair of rectangles associated with the words for whatever reason. And let's just rerun this code. I always make my second rectangle lowercase for some reason. Alright, no surprise. Value of hello is a rectangle that's 5 by 6. Value of bye is a 2 by 3. Value of haha is null. And when we print the entire hash map, we see, right, all of this stuff. This should be pretty miraculous, right? We're saying, you know, print hash equals plus hash. Well, what's happening to make this line appear? The system is calling hash.toString, and toString is going through, iterating over the elements of the hash, so, you know, going through your array if you were writing this and looking for things that are not empty, and printing out the string, and then to print out the data associated with it, it calls that data's toString method. Well, since that data is a rectangle, right, the item associated with this key is a rectangle, it calls that rectangle's toString, which is the code that we wrote, which says, go ahead and return a string containing rect, height, x, width. And all of that comes together, and we get this nice output here. Let's make it even weirder. Let's make a hash table which is keyed off of rectangles and stores. Let's key off rectangles and store rectangles. Why not? So let's store a 3 by 5 rectangle, and let's associate with it a 5 by 3 rectangle. And let's put a 4 by 4 rectangle, and let's associate it with a 1 by 1 rectangle. And let's put a 5 by 7 rectangle and associated with it a 5 by 7 rectangle. And let's just print out the value of, let's say, this 4 by 4 rectangle. I honestly don't know if this is going to work, fail, or cause the universe to be sucked into a black hole. So we're going to call the get function on hash, and we're going to specify a key, which is a 4 by 4 rectangle. What I'm not sure is if it has to be the same key, the same 4 by 4 rectangle as this one, or if it will simply look at a 4 by 4 rectangle. I think it actually has to be this, this 4 by 4 rectangle. But let me just do this really quickly, and then we'll do it the right way. Yeah, so something like this. Oh boy, what did I do? I got 3 minutes. We can do this. Alright, so we'll make 3 rectangles, R1 through R3. We will add some data associated with each of those, and the data we're adding is a rectangle. And the data we're adding for R2 is actually just a 1x1 rectangle, right? Default constructor. And so when we try to get that using the get method, we should get back a 1x1 rectangle. I think I got other issues there. Can I find symbol hashdot? I was doing this last night too. So it's the put method and the get method. And then if we run this, element at R2 is a rectangle, which is 1x1. And if we just call the toString method, we get our nice description of our hash, which says there's a key, which is a 4x4 rectangle, and the data associated with that is a 1x1. There's a 3x5, and the data is a 4x5. There's a 5x7, and the data is a 7x5. So this is uber powerful, right? Totally general purpose hash table, any type of key, any type of data. Okay, so PA2 we'll talk about tomorrow. Our keys are going to be strings, our data are going to be linked lists of integers, and we're going to redo our word index program that we dabbled in 224 to see where words occur in a set of text, like war and peace. All right, so that'll be our focus tomorrow, is going through PA2 and seeing how all this stuff can apply to it. And it's a fun program, okay, because most of the work is done for you. You get to put the blocks together and make something really cool. All right, that's 10:50. I will end here for now. I will see you next time.